For a long time, we have looked to the stars for answers. We have searched for planets that look like our own. We call them Earth-like planets. The idea was simple. We thought life needed a planet that was just like Earth. It had to be the right size. It had to be the right distance from its star. This search has led us to many fascinating worlds far beyond our solar system. But what if we have been looking in the wrong places all along? What if the best real estate for life isn't on a planet at all? This is a new and exciting idea in science. Scientists are now turning their attention to moons. Yes, the very same kinds of objects that circle our own planet. These are not the barren, dusty worlds we once imagined them to be. Some moons in our solar system are dynamic and active. They have features that could make them perfect homes for life. This has changed our whole perspective on where to search for extraterrestrial beings. We're starting to think that moons could be even better candidates for life than many planets. For decades, we have been obsessed with something called the habitable zone. You might know it as the Goldilocks zone. This is the area around a star where conditions are just right for liquid water to exist on a planet's surface. Earth sits comfortably within our sun's Goldilocks zone. This is why we have vast oceans teeming with life. But the moons of our outer solar system are rewriting the rules. Take the moons of Jupiter and Saturn, for example. They are very, very far from the sun. First up is Europa, one of Jupiter's largest moons. At first glance, Europa looks like a giant cracked billiard ball. But scientific data suggests that beneath Europa's icy shell, which could be 15 to 25 kilometers thick, lies a massive global ocean of liquid water. Next, we travel to Saturn to visit a much smaller moon called Enceladus. The Cassini spacecraft made a startling discovery: huge plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole. These geysers are shooting material from a subsurface ocean straight out into space. Then there is Titan, Saturn's largest moon. It has a thick, hazy atmosphere, even denser than Earth's. Unlike Europa and Enceladus, Titan's surface is not covered in water ice, but it has lakes, rivers, and seas of liquid methane and ethane. When we think of planets, we imagine huge, massive spheres. For a long time, we thought size was a key ingredient for life. Moons are, by definition, smaller than their parent planets, so we often overlooked them. But it turns out that being small isn't necessarily a disadvantage. Their small size allows them to be dramatically affected by the gravity of their massive host planets. The constant gravitational tugging creates tidal forces that knead and warm their interiors. Location, location, location. In real estate, it's everything. In the search for life, we used to think the same thing. But moons have taught us that a good location can mean something else entirely. It's not about being near a star. It's about being near a giant planet. Being in orbit around a gas giant like Jupiter or Saturn puts a moon in a very special place. It places them within the planet's powerful magnetic field. This magnetic field acts like a giant invisible shield. It deflects a huge amount of dangerous radiation that streams from the sun and from deep space. When we look at planets, we often focus on their surfaces. But for many worlds, the surface is a dangerous place. Life on the surface needs a thick, protective atmosphere to survive. Earth has one. Moons offer a brilliant solution to this problem. Instead of a blanket of gas, they use a blanket of ice. This creates a hidden world where the temperature is constant and conditions have remained unchanged for billions of years. Let's start our tour with one of the most famous moons in the solar system. Its name is Europa. Beneath Europa's icy shell lies a vast global ocean of liquid water. This ocean could contain more water than all of Earth's oceans combined. It's possible that similar vents exist on Europa's seafloor, providing energy for life. So, Europa has all the key ingredients we think are necessary for life. Now let's travel from the Jupiter system to the realm of Saturn. Here we find a much smaller moon, but one that is just as exciting. In 2005, Cassini flew past Enceladus and saw something breathtaking. Giant plumes of water vapor and ice crystals were erupting from long cracks near the moon's south pole. Cassini was even able to fly through these plumes and sample them directly. It was like getting a free taste of a subsurface ocean without having to land and drill through the ice. The plumes contained not just water, but also salts, silica dust, and complex organic molecules. Our final stop in this tour of promising moons is also in orbit around Saturn. Meet Titan, Saturn's largest moon. Thanks to the Huygens probe and years of radar mapping by the Cassini spacecraft, we have finally pierced through the smog. It has a weather cycle similar to Earth's water cycle, but with hydrocarbons. Methane evaporates from the seas, forms clouds, and rains back down. Could life exist on Titan? If it does, it would have to be completely different from anything we know. The potential for life on these moons depends entirely on the chemistry of their hidden oceans. It's not enough to just have liquid water. This process, called serpentinization, can release hydrogen gas. On Earth, microbes in the deep ocean combine this hydrogen with dissolved carbon dioxide to create energy. The data from Cassini's flybys of Enceladus strongly supports this idea. The plumes were found to contain molecular hydrogen and carbon dioxide, the very ingredients needed for this type of metabolism. This is what makes these moons so compelling. They're not just passive pools of water, they are dynamic chemical reactors. How can a tiny moon, billions of kilometers from the sun, stay warm enough to have a liquid ocean? The answer is not sunlight, but gravity. Imagine holding a small rubber ball in your hand and squeezing it repeatedly. The ball would stretch and deform, and if you did it fast enough, the friction inside the rubber would make it warm up. As a moon like Europa orbits its planet, it's constantly being squeezed and stretched. This relentless cycle of being pulled and relaxed creates immense friction deep within the moon's core and mantle. This internal furnace is what keeps the moon geologically active. This heat radiates outwards from the core, providing enough sustained energy to melt the bottom of the thick ice shell. Liquid water is the one ingredient we consider absolutely essential for life as we know it. Every living thing on Earth, from the smallest bacterium to the largest whale, depends on it. But the icy moons have shown us there is another way. They have hidden their water away, protecting it under a thick, solid lid of ice. This ocean is trapped between the rocky core at the bottom and a thick, insulating shell of ice on top. It's a hidden habitat, a world within a world. The universe may be teeming with these hidden ocean worlds, each one a potential cradle for life. So we have heat and we have water. But life needs one more thing: energy to power its metabolism. On Earth, most life gets its energy from the sun through photosynthesis. But in a dark ocean, hundreds of kilometers beneath a shell of ice, there is no sunlight. So could life exist there? The answer lies in chemistry. Life can be powered by chemical reactions, a process called chemosynthesis. This happens on Earth in the deep, dark ocean around hydrothermal vents, and the same thing could be happening on icy moons right now. This creates a rich chemical soup full of potential energy sources. On Earth, microbes thrive around these vents by using the chemical energy stored in molecules like hydrogen sulfide. This is a profound realization. It means that life doesn't need a star. It just needs a geologically active world with the right chemical mix. There is one last piece of the habitability puzzle that gives moons a special advantage: protection from radiation. The universe is filled with high-energy particles. Earth has one in its global magnetic field, which creates a protective bubble around us called the magnetosphere. But a moon orbiting a gas giant gets protection for free. Gas giants like Jupiter and Saturn have monstrously large and powerful magnetic fields, way stronger than Earth's. So really, the combination of the magnetosphere and the ice shell provides complete protection. This means the subsurface ocean is one of the most shielded, stable places in the entire solar system. When we compare planets and moons, we see that moons offer some unique advantages in the quest for life. The biggest advantage is stability. But on an icy moon with a subsurface ocean, the environment is incredibly stable. Underneath a thick ice shell, the conditions are timeless. Another key advantage is the protection offered by that same ice shell. The kilometers-thick ice provides a physical barrier that is far more effective at blocking radiation than most atmospheres. These moons offer a set-it-and-forget-it style of habitat, where the conditions for life, once established, could persist for cosmic timescales. Of course, living on a moon is not without its difficulties. The tidal heating that warms their oceans is actually a violent process. Another major challenge is the limited access to certain elements. A subsurface ocean on a moon is a much more isolated system, Energy is another potential bottleneck. The total amount of energy available in a dark ocean would be tiny compared to the energy the sun pours onto Earth's surface. So this might mean that if life exists on these moons, it could be very sparse. We might only find simple microbial life, living slowly in the dark. When we weigh the pros and cons, it becomes clear that moons force us to rethink what just right really means. For a moon, being just right means having the right-sized orbit around the right-sized planet to generate the perfect amount of tidal heating. The universe might have two main blueprints for life: the sun-drenched surface model like Earth, and the dark, tidally powered ocean model like Europa. This realization actually doubles the potential places we can search. It's a thrilling prospect that suggests habitable worlds could be far more common and varied than we ever dared to imagine. Our cosmic search has taken an exciting turn. For generations we gazed at planets hoping to find a twin of our own world. But the moons of our own outer solar system have shattered these old ideas. Moons like Europa and Enceladus offer a new blueprint for a living world. This realization has fundamentally changed our strategy in the search for extraterrestrial life. We're now designing missions to visit these icy moons right here in our own cosmic backyard. Their hidden oceans could be the most common type of habitat in the galaxy, far outnumbering the sunny, temperate surfaces of worlds like our own. What comes next in this grand exploration? Missions like NASA's Europa Clipper and the European Space Agency's JUICE are already on their way. The ultimate goal is to land on the surface and go for a swim. Future missions are being designed that would include a lander, one that could drill or melt its way through the ice shell. Imagine a submersible gliding through the dark waters of Europa, its headlights revealing a world that has been hidden from sight for billions of years. Whether we find microbial life, complex creatures, or nothing at all, the search will teach us about the conditions that make life possible. These icy moons have opened our eyes to a whole new class of habitable worlds. They have expanded our cosmic perspective and given us new hope. The journey to unveil their secrets has just begun, and the discoveries that await us will undoubtedly change our world forever. The answer to one of humanity's greatest questions might be waiting for us, sealed beneath a miles-thick layer of ice, in the cold, dark reaches of our solar system.